Alright guys, welcome to our channel once again. In this video, you'll learn about electrical network analysis, KIRCHHOFF'S law. So this is the principle guiding how electrical circuits with more than one path for the flow of current can be connected to an equivalent single path circuit. So usually we make use of Ohm's law for this. But however, there are more complicated circuits which cannot readily be reduced to one single equivalent circuit for this Ohm's law. In such case, we actually use the KIRCHHOFF'S law or the KIRCHHOFF'S rule, which is more like a generalized form of the Ohm's law. Alright, so KIRCHHOFF'S first rule is based on the law of conservation of charge. And this law states that the sum of currents flowing into a junction is equal to the sum of the currents flowing out of it. So I would like to illustrate this using this simple diagram. So remember, we said the sum of currents flowing into a junction is equal to the sum of currents flowing out of it. So let's say this is a junction in a connection. So let's say we have the first current flowing into this junction from here. So this is I1, but then there are currents also flowing out of it. Let's say this is I2, and then flowing out through this way is I3, and then flowing out through this way is I4. Now, if we have something like this, according to the KIRCHHOFF'S first rule, we can say that I1 is equal to I2 plus I3 plus I4. So this is simply what you get. Now let's talk about the second rule. The second rule, on the other hand, actually deals with the potential drop across the resistor in the circuit, and is based on the law of conservation of energy. So I'll go ahead and write this, then I'll state the law. So the second rule, or the second law, states that the sum of average drops in all resistance in a closed circuit is equal to the sum of EMFs in the circuit. So we can simply illustrate this mathematically by saying IR, or sum of IR, is equal to sum of the EMFs. So the two rules we've discussed above allows us to calculate the currents flowing through each branch and or the potential drop across each resistance in a closed circuit. So in order to actually make calculations using this, we have to employ these processes. So first of all, we have to assign a direction to the flow of each branch of the current. And then the second process is to identify each closed loop and design a direction for adding up the EMFs and the potential drops around each of the closed circuits. So I'll show you how to do this. I'll have to get this example down here. So looking at the diagram here, okay, the question says find the currents I1, I2, and I3 in the circuit shown below. So looking at this diagram, you can see we have the 10 ohms resistor here, we have a 10 ohms resistor here, we have 3 EMFs here. So you can see that there is current flowing along these paths. So we are going to actually determine the currents here for here, and for here. Alright, so the first step, like we mentioned earlier, is to assign a direction to the current in each branch of the circuit. So with this, let's say we have the current flowing through this, into this, flowing here, into this, and flowing out this way. So we'll get that if we make this the reference point, if we make A here, point A here, the reference point, we will realize that the current here, which is I1, and then the current here, which is I2, and then the current here, which is I3, we can actually generate a rule for these three currents. Now, because I2 is moving towards this direction, and then I3 is moving towards this direction, and then I2 is moving. So here, we're going to identify the direction of flow of currents. Sorry, there should be a note here. So let's say current I1 is passing through this point. So this is the direction of flow. And let's make A here our reference point. Let's say I1 is moving towards A. And then I2, or I2 here, I2 is moving away from A. So let's call this I2. And then I3 is moving also towards A. So we have I1, I2, and then I3. So now we can tell that from this we can actually generate our Kirchhoff's rule for this. Now since this current is moving towards the point, this one is moving towards the point, and this one is moving away from the point, it means that I2, which is moving away from the point, is equal to I1 plus I3 according to the Kirchhoff's rule. Alright, so the next thing we are going to do is to consider a closed loop for these points and then for these points. So you can see that there are two possible loops here. One is this and the other is this. So we have one here. Now remember we are making A our reference point. So let's say this is A. Okay, let's name this point D in the diagram. So this is A, D, B, A. That's our first reference point. And then we have our first loop rather. We have our first loop A, D, B, A. And then we have our second loop A, C, D, A. So we have two loops now. Loop 1 is A, D, A, B, B, A. And then loop 2 is A, C, D, A. So A, C, D, A. So what are we going to do here? We are going to actually find the voltage drop across by making use of the Kirchhoff's rule here. So normally we have from our rule, we said for our procedures rather, we said in procedure 2 we have to identify each closed loop and design a direction for adding up the EMFs and the potential drops around each closed circuit. So how we are going to do this is we are going to actually use any convenient means that works for us. Now if you look at the EMF here, you'll notice that there is a positive terminal and there is a negative terminal. So if the flow is going from positive to negative, and you want to make all the flows in this direction become positive, it means all the flows in that direction will become positive, and all the flows opposite that direction becomes negative. Or you can actually make all the flows in this direction that's positive to negative become negative, and then all the flows in the other direction, negative to positive, becomes positive. So another thing is, all the resistance flowing in your direction you've chosen should be either negative or positive. So if you're using negative, it means all the currents you're going to use should be negative. And if you're using positive, it means all the currents you're going to use should be positive. So having said that, so we're simply going to apply our second rule according to Kirchhoff's rule. So what we are going to do here is we are going to recall the rule. Remember, the rule says identify each closed loop and then design a direction for adding up the EMFs and the potential drops around each closed circuit. So what's the potential drop? First of all, the current times the resistance, and then what's the EMF? That's the voltage you have here. So I have 8 volts here, I have 6 volts here, and I have this current times the 10 ohm. Alright, so what we're going to do is we've actually designed the direction of flow, which is this way. We've taken this way, this direction, to be the direction of flow in this circuit. So the next thing we're going to do is, now if you notice the EMFs, you will see that they have polarity. So one is long, this is short. So this is positive, this is negative. So using your direction of flow of current, you can decide that when you go from positive to negative, you have a negative. You can also decide that when you go from positive to negative, you have positive. But whichever you use, always try to be consistent. So you can also, on the other hand, decide that when you go from negative to positive, you become positive, or when you go from it becomes negative. So pay attention to this. We'll use this to verify some. We'll use this along in our course of calculation. So now what we are simply going to do is we are going to take a particular step here. So let's consider this closed loop. This is A, B, B, A. So this is the direction of flow. So we can simply go ahead and say, when we go from positive to negative, let's have a negative value. So it means any direction we are choosing, we have to be very much consistent with it. And then we can also, on the other hand, say that the potential drop, once you are following this direction, will always be positive or negative, as the case may be. So let's, in this case, should we use positive? Right, let's use negative. So let's say the potential drop will always be negative as long as we are moving towards this direction that we've chosen. So at every instance you make the potential drop negative. All right, So having done that, now let's go. We are moving from A to D, and this is 8 volts. So let's say we are making it negative and consistently. So since we are moving positive to negative, let's say this is negative. So from A here to D here, we have minus 8 volts. So minus 8. And then from D to B. Now, look at this. We are moving from negative to positive. So we'll have to change to positive. Now, it's an opposite direction of this. We're moving this way. So it has to be positive. Remember when we moved from positive to negative, we had a negative value. Now we are moving from negative to positive. So we'll have a positive value of this, which is plus 6. And then remember we said we want to make all our potential drops negative. So we have this moving towards this, we'll have minus 10I. That's the current times the resistance. The resistance is 10 ohms, and then the current is not given. Alright, so when we have all this, we equate it to 0. Alright, so when we make further calculation of this, we will have 10I to be minus 2, and then I alone to be minus 0.2 amperes. Alright, so I'll go ahead and wipe these other parts so we'll have more space. Let's wipe this area off. Okay, so the next is the second loop here. So remember we are considering all potential drops to be negative, and then since we are considering all potential drops to be negative, I have minus 16I, minus 16I. Now here we're moving from positive to negative. So what's that? Minus, right? Minus 12 volts. And then from here we're moving negative to positive. And what should we have here? A positive sign. That's plus 8, right? Alright, so these together gives us 0. So we are equating this to 0. So when we equate this to 0, we can actually find I. Okay, so over here we can simply say, alright, let's recall that the I here is the one across this, and that's I2, whereas the I here is the one across this, which is the I1. That's I1. Alright, so to find I2, we can simply say that 16I, that 16I2 is equal to minus 4, right? So I2 is minus 4 over 16. That's minus 0.25, right? Yeah. Alright, so since we've gotten the values of I2 and I1, we'll go ahead and impute it in our first equation. So let's go ahead and wipe this. So let's recall I1 is 0.2 and I2 is 0.25. So let's go ahead. We have our I1 to be 0.2. I2 is 0.25. So now when we want to impute these in this equation, replace I2 by 0.25. So this is minus 0.2 and minus 0.25. So replace I2 by minus 0.25. So go ahead. So go ahead and write minus 0.25 is equal to I1, which is minus 0.2, then plus I3, which is unknown. So to get I3 here simply should be I1 minus I2, where our I1 is minus 0.25 and I2 is minus 0.2. So if we go ahead and calculate for this, I3 should be minus 0.25 minus negative 0.2. Alright, so here, if I have our I3 to be this, we can change this to positive. So we'll say negative 0.25 plus 0.2. So when we add up this, we have our I3 to be 0. minus or negative 0.05. Alright guys, so we've come to the end of this lesson today. If you enjoyed this video, please click on the subscribe button if you are not yet a subscriber. So ensure to like and share the video with your friends. Also drop your questions on the comment section below. Thank you. See you next time.